In this video, we will consider the Chisquare test for goodness of fit and also Chisquare test for independence of characteristics. So, fitting of a distribution is a principle of obtaining a mathematical equation to address a random phenomenon. We found that in fitting of binomial distribution, we will be given a frequency table and there will be a random variable x in the frequency table. It values some 0, 1, 2, etc., some 7 and the frequencies in the next column. So the randomness of the variable x can be addressed by fitting a binomial distribution to the data. In order to fit a binomial distribution to the data, we have to determine the constant p of that binomial distribution, and that can be estimated using some principle of estimation techniques, that is moment estimation or maximal likelihood estimation. So in moment estimation, we have found that p is equal to p cap is equal to x bar by n. So after finding the sample mean of the given data, we can obtain an estimate of p as p cap equal to x bar by n, and thus we have the complete equation of the binomial distribution given by this ncx p raised to x q raised to n minus x. Thus, fitting of a distribution consists of proposing a mathematical equation to the given data or to the given frequency table. So we can fit a binomial distribution to a given data, or if that fit distribution may be Poisson, or if the variable continuous, we can fit a normal distribution to the data. So that is the process of fitting of a distribution. Now, after fitting the distribution, here we can identify whether the model proposed is good or not. For that, we can make use of Chisquare test for goodness of fit. Here, this Chisquare test for goodness of fit can be used to test whether the population values follow certain distribution or they agree certain proportion or ratio of occurrences. So here we have set of two sets of frequencies. One is observed frequencies and the other is expected frequency. The observed frequencies are the frequencies directly we get from the field. That is, after conducting the survey, we can get the frequency of each class, that is denoted by, they are denoted by OI. So O1, O2, etc. ON are the frequencies of n classes. Now, making use of the equation proposed, that is the distribution or the ratio proposed, we can obtain the theoretical frequencies of each class. That is, EI represents the ith expected frequency of ith class. So OIs and DIs are the observed and expected frequencies. Observed frequencies are the frequencies we directly get from the survey, and expected frequencies are the frequencies obtained under the assumption that the variable follows such and such distribution or that agree the ratio or the proportion proposed. Thus, the test is to examine whether the population is in perfect agreement with that distribution or that population follow exactly the given equation. For that, we have the test statistic. Chi-score equals sigma is equal to 1 to n OI minus EI square divided by EI. Here, the null hypothesis is that the population is in agreement with that population distribution or the proportion proposed. Therefore, if that is in perfect agreement, if the null hypothesis is true, the OIs and EIs will coincide each other. Therefore, if the null hypothesis is true, the value of chi-square will be 0 since OIs and EIs coincide each other. Therefore, we set the null hypothesis as at 0 chi-square equal to 0. Now, if at all this chi-square is not 0, we are ready to accept this population follows such distribution or the proportion is valid. So we have to get a limit within which we can accept the hypothesis, and therefore this is using the test for, now this is using the tables of chi-square distribution. Also note that this value of chi-square equal to 0 in h0. But since chi-square is always a positive valued random variable, this left side test is not valid here. That is no h1 chi-square less than 0 or no h1 chi-square not equal to 0. Therefore, the test for goodness of it is always a right-sided test. That is h0 chi-square equal to 0 versus h1 chi-square greater than 0. Now, the critical region corresponding to the alternative hypothesis h1 chi-square greater than 0 can be obtained from this tables of chi-square distribution. Since this is a right-sided test, we set this critical region in the right side of the frequency curve. That is, in the chi-square frequency curve, we can see that in this application of chi-square distribution, we have the frequency curve of chi-square distribution for a right-sided test. So here this chi-square greater than 0 or right-sided test has the critical region chi-square greater than chi-square alpha, where chi-square alpha is the coincidence of the degrees of freedom and also the probability alpha. Therefore, the critical region appears in the right side. Therefore, here the critical region is chi-square greater than chi-square alpha, where chi-square alpha is corresponding to degrees of freedom k minus r minus 1 and probability alpha. So what is k minus r minus 1? K is the number of classes after pooling. So what is the pooling? Pooling is the process of combining adjacent classes if any class has an expected frequency less than 5. So if there are n classes and there is one class with less than 5 expected frequency, that class has to be combined with or pooled with the adjacent class. Therefore, k is the number of classes after such pooling process. So k can be maximum n, or if one class pooled with adjacent class, then k will be n minus 1 and so on. So we have to keep on pooling the classes, adjacent classes, so that the expected frequency is greater than 5. So when we pool this with reference to the expected frequencies, the observed frequencies also should be combined. Now that's about the k, that is the number of classes after pooling. R is the number of parameters estimated using the sample. In the case of binomial distribution, if you are finding P or estimating P using the sample data, then R will be 1. In the case of fitting of normal distribution and testing the goodness of fit, there we have to determine two constants mu and sigma square from the data. Therefore, R will be 2. So in short, R is the number of classes. Now, R is the number of parameters determined using or estimated using the data given. You know, in the case of testing the validity of a proportion, we don't need the data to estimate expected frequencies, and therefore R will be 0. Generally speaking, that k minus r minus 1 is the degrees of freedom, k is the number of classes after pooling, and r is the number of parameters determined using the sample. Therefore, the critical region is given by chi-square greater than or equal to chi-square alpha, where chi-square alpha is the coincidence of the row corresponding to k minus r minus 1 degrees of freedom and probability alpha. That's about test 4 goodness of it. The next application of chi-square distribution is for testing independence of characteristics. Here we will consider two characteristics A and B. So we have m levels of A and n levels of B. So there are mn cells, m into n cells. So this is known as a contingency table, and the entry corresponding to the ijth cell represents the number of units in the sample possessing ith level of A, the characteristic A, and jth level of the characteristic B, that is OIJ. OIJ is the observed frequency of ijth cell. Now, here our aim is to examine whether the two characteristics are independent or not. The two characteristics are independent or not. Here we have the totals, that is sigma j is equal to 1 to n O1j, sigma j is equal to 1 to n O2j, etc. So sigma j is equal to 1 to n OMJ. They are the raw totals, and then here in the bottom row represents the column total. Sigma I is equal to 1 to m OI1, I is equal to 1 to m OI2, etc. The total of the row totals or total of the column totals will be equal to the total frequency. Now, the null hypothesis is that these two characteristics are independent. So we said the null hypothesis that the levels of characteristic A and levels of characteristic B are independent to one another. So here the test statistic is sigma is equal to 1 to m, sigma j is equal to 1 to n, Oij minus Eij square divided by Eij, where chi-square follows chi-square distribution with m minus 1 into n minus 1 degrees of freedom. Here Eij is the expected frequency of the ijth cell. We can calculate this expected frequency of ijth cell under the assumption that the two characteristics are independent. For that we have the equation Eij is equal to sigma is equal to 1 to m Oij into sigma j is equal to 1 to n Oij divided by n. That is, the ijth cell expected frequency is obtained by the product of sum of the ith row and sum of the jth column divided by total frequency. This is using the property that probability of A intersection B is equal to probability of A into probability of B when A and B are independent. So if the data, if the levels of the two characteristics are purely independent, we get Oij and Eij equal. So Oij's and Eij's will coincide each other for all Ij cells, m into n cells. So therefore, this null hypothesis, the two characteristics are independent, can be remodified as this H0 chi-square equal to 0. That is, the value of chi-square will be 0 if the data and other levels of the two characteristics are perfectly independent. Now note that this H0 chi-square equal to 0 if the null hypothesis. The alternative hypothesis is H1 chi-square greater than 0 because chi-square value cannot be less than 0. So there is no left-sided test and also no two-sided test. Therefore this test is also a right-sided test. And this chi-square statistic has degrees of freedom m minus 1 into n minus 1. So the critical region corresponding to this alternative hypothesis H1 chi-square greater than 0 is chi-square greater than chi-square alpha, where chi-square alpha is the is from tables of chi-square distribution. It is the coincidence of the m minus 1 into n minus 1 degrees of freedom and the probability alpha. Therefore, we reject the null hypothesis if the value of chi-square calculated using this equation is greater than the value we refer from tables, that is chi-square alpha. So this is the rejection region, and we conclude that the two characteristics are not independent. The assumption is the null hypothesis is the two characteristics are independent. If we reject the hypothesis, we conclude that the two characteristics are dependent. That's about the test for chi-square distribution for independence of characteristics. Thank you.